Hi everyone, let's talk about waves. You're familiar with waves like ocean waves or ripples on a pond or maybe light waves. Well, all waves can be described in a number of different ways. Here's a little diagram here. We can talk about the wave vibrating up and down, and the distance between the up portions of the wave is called a wavelength, and that should be the same as the valleys of the wave. That's the same wavelength. Energy is carried by waves in two ways. You can talk about the height of the wave. So if the wave gets much bigger, up and down, that's also called the amplitude, then it's a stronger wave. But you can also vibrate it faster, and that's frequency. So this wave here, if it takes 1 second to complete, what is this, 3 oscillations, starts here, goes down, goes back to its starting point, that's 1 complete vibration. And then we go again, that's 2, and then 3 times, sure, that's 3 times per second, and the units of per second is called hertz. So the frequency here is 3 hertz. And you may have heard of megahertz. That's on the radio dial, AM and FM dial. And that's the same type of hertz. So radio waves, there you go, radio waves, they have frequency and wavelength and amplitude. The speed of the wave can be calculated if you know both the frequency and the wavelength. You simply multiply them together. So here's someone throwing a pebble into the pond. As the pebble strikes the water, it creates waves. The surface of the water moves up and down. And if you look at the distance between each up part of the wave, that's your wavelength. The speed at which it propagates out from the center is the wave speed. And how quickly it vibrates up and down, leaf bobbing up and down with the frequency of the wave. Now, frequency and wavelength are interconnected. Here's a turtle moving very slowly, so it's a very slow frequency, very low frequency, and that causes large waves. So the wavelength is really big. The rabbit here is vibrating much more quickly, so the frequency is higher, more vibrations per second. That causes smaller wavelengths. So frequency and wavelengths are oftentimes opposites. There are 2 types of waves. They're the waves we think about on the ocean or on a pond, which travel up and down. And so the vibration is up, down, but the direction that the wave moves out or propagates is at right angles to that. That's a normal looking wave. Those are called transverse waves. But you can also have waves that vibrate within the same direction of motion. So here's a slinky, and this person's pressing it in and stretching it out, and you get parts of the wave that are compressed and parts of the wave that are expanded. And so that's a wave too, and it moves in the direction that it's vibrating. Those kind of waves are called longitudinal waves. It turns out that sound waves are actually longitudinal waves. So you're listening to this recording because your speaker is vibrating, and it sometimes presses out and compresses the air, and so the air gets all compressed, and then it drops back and creates a low pressure region of air. It kind of expands air, so it gets expanded, and then these packets of compressed and expanded air travel outward from the speaker and reach your ear, and then those areas of high pressure and low pressure strike your eardrum and make your eardrum vibrate, and you perceive that as sound. Maybe you're familiar with the tuning fork. It's a piece of metal shaped in a U, and it's very stiff metal, and you can kind of strike it gently against an object and get the fork up here, the tuning fork, to start vibrating. And if you slow it down and kind of watch in slow motion, as the fork spreads out, it presses the air before it. So you get a portion of the air that's under higher pressure, compressed, and then the bars of that tuning fork will come back in, and next to the tuning fork, that part of the air will experience low pressure and be expanded or rarefied, is the scientific term. And then these regions of high and low pressure extend outward. And as it vibrates quickly, well, you get higher frequencies of these compression and rarefication regions. And then the sound wave propagates outward. Now, the speed at which sound travels depends on the medium or the material that the sound is propagating through. So if we think about sound traveling through air, well, air is pretty thin, right? So as the air molecules get compressed, they travel outward, they have to compress the air in front of them, and then the low pressure region comes and expands the air, and it takes a little bit of time. So sound traveling through air measures about 330 meters per second, translates about 730 miles per hour. If you jump into the swimming pool, you can still hear sound underwater, and it turns out sound travels much more quickly through water because water is more dense than air, and so these regions of compressed water and expanded water, they can travel more quickly because the material is denser, and the sound can propagate more effectively through it and more quickly. So about 1,500 meters per second. And, if you tap on a wall or tap on a copper pipe, sound travels even faster because those materials are even more dense, more solid actually, than water or air, and the speed of sound increases up to 5,000 meters per second. Light is also a wave, and light is one of the fastest things we know of, traveling roughly 300 million meters per second. And that's a lot of zeros. So remember the use of scientific notation. We can write this same number as 3 times 10 to the 8th power. And then if we use the same units, well, let's use miles per second. Light travels really fast. It's 186,000 miles per second. And in comparison, sound is only 0.2 miles per second. That's about 1/5 of a mile every second. So I don't know if you did this as a kid. My mom and dad told me about this, that if you're watching lightning outside, you're kind of scared at night. What you can do is see the flash of lightning, and light travels really, really fast, almost instantaneously. So the moment you see lightning, you start counting the seconds. I don't know, 1 Mississippi, 2 Mississippi, however you want to count your seconds. When I used to play, flag football, we used to go 1 alligator, 2 alligator. Well, count your seconds, then the number of seconds that it takes for you to hear the thunder can tell you how far away the lightning struck. So start counting the seconds, and since sound travels 1/5 of a mile every second, it takes 5 seconds to travel 1 mile. So watch the lightning strike, start counting the seconds, and every 5 seconds tells you that the lightning is 1 mile away. So we used to get kind of scared as we started counting the seconds after lightning struck. If we counted fewer seconds, we realized the lightning was coming towards us. But as the storm progressed, we could hear the lightning kind of recede away. We see the lightning, and it would take longer for the thunder to reach our ears. And then we knew that the storm was passing. Okay, last topic for Chapter 10, the Doppler Effect. Okay, this is a change in frequency due to the motion of the source of the wave or by motion of the observer of the wave. So here we got a police car. It's in motion. We got 2 bystanders here. And as the police car is driving away from the lady here, the sound waves generated by the siren appear to be expanding. That takes longer for each wave to reach the lady. And so that makes for a lower frequency, longer wavelengths. Remember, wavelengths and frequency are kind of opposites. So really big waves make for low frequencies, slower up and down motion. Well, sound waves, so compressed and expanded regions. But if you're in front of the car, as the sound waves are generated, the car kind of catches up to the wave in a sense and generates a next wave of sound. And now these waves are more compressed together. They have shorter wavelengths. Small wavelengths, well, that's opposite. We get high frequencies. And that's the Doppler effect. And it works not only for sound, but also light. It works for all waves. Well, let's look a little bit at a video to explain it in motion. It's kind of nice to see it as a video rather than as an image.
So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency.
So if I pause the video, you can see that the waves in the shaded region on the left are closer together, right? So the top of the waves, that's what these circles represent, they're closer together. The wavelengths are shorter, which means the frequency is higher. They're vibrating more quickly with respect to people listening to the sound or looking at the light wave on the left. Now if we look on the lighter region on the right, these waves are farther apart. The wavelengths are longer and the frequency is lower. So you get a lower pitch. And on the left side, it's a higher pitch, a higher frequency. So if you watch The Big Bang Theory, Sheldon is going to describe the Doppler effect.
I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. Most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Thanks, Sheldon. He explained the Doppler effect better than I did. Okay, that's all for now. Thanks for watching.